All right, good day, guys. You're welcome again. And today we'll be taking on, as one of the modules in the structural design course, we'll be taking the calculation for the tensile capacity of a steel section. All right, so in previous lessons, we've been able to check for shear, bearing, and block shear also. Okay, so going forward, we want to look into the determination of the tensile capacity of this section. Okay, so we have an example here above, and it says that a single angle tension member, angle iron, of course you can see 100 by 100 by 10, made from S275 steel, is connected to a gusset plate of 8 mm thick with 20 mm diameter bolts as shown in the figure. Alright, so the factor axial tension due to dead load and live load are 150 kilonewton and 65 kilonewton respectively. So we are expected to calculate the tensile capacity of the section and check if it is safe for the load given. And in this example, I'll be dealing with question 1, and question 2 is more like a repetition of those things we have done previously in other modules. But I will require that you solve them and get it across to me so that I can verify whatever it is that you've done. Alright, straight to what we need to do for today. Okay, we are supposed to determine the tensile capacity. Tensile capacity. Now we can get this from clause 4.6.1 of our BS 5950. So let's go there for reference purposes. Okay, so clause 4.6.1 truly speaks of the tension capacity. Now it says the tension capacity PT of a member should generally be obtained from this relation. This is a general formula for obtaining the tension capacity. So we may want to just have that pen down as we go ahead. PT rather, not PY. PT is equals to PY AE, and all of these parameters have been defined from in the BS code. All right, so we have PY to be the design strength. Okay, then we have AE, which is supposed to be the sum of effective net area of all the elements in the cross section. Okay, all right, so the next thing we're supposed to do is to identify what section we are dealing with. Now in this case we are dealing with an equal angle, all right, 100 by 100 and then by 10, and it says it's S275 steel. So if we're going by what we have here, but do not forget the code already told us that this is just a general formula. It's a general formula. Are you there? So but we are dealing with an angle iron in this case, and we are dealing with a simple or single angle tension member. It is not of other conditions. So there are different things that has to do with when you are dealing with simple tension members like single angle or T-section member. So we are dealing with single angle member. So you know that the tension capacity is not going to be determined by the general formula, just by the general formula, but we are going to check for whether it is a bolted connection or a welded connection. Then we can pick our references from here. Okay, so in this case this one would actually suffice and not the general formula, because this was a bolted connection of a single angle tension member. Okay, so let's get this formula also down written. So I've been able to clarify why we can't use this formula, and then we have to stay with the other formula. Okay, and the other formula I showed you states that PT is equals to PY AE minus 0.5 A2. Okay, so let's get to work. This PY is the design strength, and I told you that the design strength is actually dependent on the thickness of the thickest element, okay, which is usually the flange. But in this case, we are dealing with single angle tension member. There is no basically web and flange, as the universal beam and all of those things. So in this case, we know that we have a small t and not a capital T. So if you check your steel designer manual, for example, let's go there and check what we have there. Steel designer manual, you have this already. I shared it with you, so you may just make references to what you have there around this part. Look for the angle line. You just have to locate the simple angle tension member. Okay, let's look for that. It's going to be somewhere below, so you have to, yes, okay, so we are dealing with equal angle, not unequal, equal angles, and it says 100 by 100 by 10. Okay, so this is what we're looking for. Now what brought us here is the thickness. Now you see that we have only the small t to be 10 and not the capital T. So in this case, you don't use the thickness of the flange to determine the strength. So the strength have been given to us in the question as 275. So that is why our PY in this case, we have affirmed that this is 10. Okay, and the PY is 275. You see that now? Okay, so, and this is an equal angle. Do not forget what I said, equal angle. In case you want to check your own steel designer manual, you look for equal angle. Okay, so to obtain our AE, which the code says to be the effective net area, okay, that's what we have here. AE is the sum of the effective net area. So how do we obtain that? And that's where we need to pay a little more attention. If you check clause 3.4.3 as recommended in this place, you see, determine from 3.4.3. So if you make references to 3.4.3, let's see what it's saying. Let's look for 3.4.3. Okay, so you see there now, our AE is equals to KE AN, where the AN is the net area of the element. Okay, so this is what we need as the formula. Now let's put that down. I showed you how I got that already. KE AN. Now KE is what from that particular code. KE for grade S275, KE is 1.2. So we are dealing with grade S275 and KE definitely is 1.2 for grade S275. Okay, then how do we obtain our net area for the whole section? How do we obtain the net area for the whole section? Okay, we are dealing with an angle iron or single angle tension member, however you want to call it. So it looks like this. Okay, connected to a plate. Okay, and then maybe we have a bolt on this side. That's exactly what our figure represents in this direction. Okay, so the gross area of this section or of this member, okay, the gross area AG. How do we obtain this? If you check the steel designer manual steel, you discover that there is the area of the section. This is what we are seeing here, area of the section, and it says it is 19.2 centimeters square. 19.2 centimeters square. So let's put that down. 19.2 centimeters square, which is equivalent to 1920 millimeters square. You see that now? Okay, so having worked this out, we'll need to also check for the gross area of connected element. You know, we have two parts. This is the unconnected part. Unconnected, that is the one that is not bolted. Unconnected. This part is the connected. This part is the connected. How do I write it now? Let me make it clear. This part is the connected part. This part is the unconnected. Okay, so we have two parts such like that. So the net area of the connected part, because the connected part now has been more like drilled and there is a void in that area already. So we need to now confirm the net area now of that particular part. The net area of that particular part. So to do that, how do we go about it? We need to first check. Now this gross area here is of the member, gross area of the section, the total section. Assuming it has not been drilled at all, this is the gross area of the section. So the next one we want to look for is the gross area of the connected part. Gross area of the connected part. Now this is obtained by subtracting the void from what we have already. So you can literally look for it with this formula. Okay, not even in this formula. Let's just make it straight. Gross area AG equals to the thickness of that member multiplied by the width of the member. Okay, and with the thickness have been given to us to be 10 and the width is 100. Remember that the dimension says 100 by 100. By 100. You see that now? Okay, so this will give us 1000 millimeter square. So this is the gross area of the connected part without anything drilled from that part. So we are dealing with this and this. Okay, so the next one we want to look at is the net area. Net area of connected leg after the holes have been removed. So we want to now remove the holes to determine what the net area would be. So that's AN. To do this, simply look for it by this relation. Because of it's a single hole. Now this is just simply saying that the total or the gross area minus the diameter that have been drilled from that particular section multiplied by the thickness. It's as simple as that. We are removing the thickness of that diameter that have been drilled off from that leg from the total area. It's as simple as that. So that would be 10 mm multiplied by the width 100 minus the thickness 10, and then the capital D. Now do not forget, I told us in the previous sections that our diameter, capital D, is the standard clearance hole, right? Diameter. So is this diameter of the bolt plus 2 mm in this case, because the diameter is 20, okay, plus 2, so we have 22 mm. You understand? So that's why this one will be 22. So AN, which is the net area, calculating all these things together should give you 780 millimeter square. So we've obtained the gross area and the net area of the connected leg. Are you with me? All right. So what we now need to calculate is the effective area of the or effective net area of the connected part. Just let's put it that way. Effective net area of connected leg. So this is the next thing we're looking for. Okay, now to do this, if you check clause 3.4.3, the one we referenced earlier here, you discover that the effective net area have been given to us, the formula have been given to us already. So we just have to just bring it back here. The effective net area is KE, and our KE have been already defined to be 1.2 multiplied by the net area 780. So effective net area of the connected leg will be 936, which is less than the gross area 1000. Remember that from this code also it says that AE has to be less than or equals to AG. Are you there now? So the next thing that we want to discuss is the area of unconnected leg. Area of unconnected leg. That is this part. Okay, so we have that. Simply you can guess what it's supposed to be. When we have the gross area already of the whole section, we can subtract the effective area of the connected leg. Then we have the area of the other part. It doesn't make sense to you. It does. So we have the gross area to be 1000. I mean 1920, not 1000. 1920. Okay. This is the gross area here of the whole section. The gross area of the whole section. Maybe I should make it clear. So this is the gross area of the whole section. It's different from this gross area of the connected part. Please do not get it wrong. So 1920 minus AE, that's for the connected leg. So that would be 984. meter square. So this is the area of the unconnected leg. So what of the total effective area now? Total area or total effective area, let's put it that way. Total effective area, AE. So that will be, this is, you can call this the net area for the second part, and you can call this the net area for the first part, however it is you want to call it. This is the net area for the first part. So you can say the addition of the first one and the addition of the second one. So net area of the first is 780, okay, plus the net area of the second one, or the effective area of the second one. So that will give us 1764. 1764. Now we've been able to obtain AE. The next thing we want to check out is straightforward to our formula, the one we started with. Now the one that is not known is A2, that we must find out before we can insert every other thing into that equation. So let's get to know what A2 represents. So from the clause 4.6, what do you call it? 4.6.1, that's true. 4.6.1. It says that A2 is the gross area of the section minus A1. And what is A1? A1 is the gross area of the connected element. Okay, so we just want to do that. A2 is AG minus A1, and this is to say 1920, the gross area, minus that of the connected part. Do not forget that that's exactly what we have obtained there. That will give us 920 mm squared. So we can go back to say that PT equals to 275, which is PY, AE 1764 minus 0.5 multiplied by 920. So this, if we're calculated, should give us 38358600 Newton, which is equivalent to 358.6 kilonewton. So PT now is equals to 358.6 kilonewton. And do not forget that in the question we're given some information. Some informations are clearly stated in the question, that the dead load and the live load are 150 and 65 respectively. So you want to actually make use of that information as we go ahead. Okay, so we know that the GK, the fact, and is factored. The QK is 65 kilonewton factored. So adding these two together, we have 215 kilonewton. Since the tensile capacity, which is 358.6 kilonewton, is greater than the load, I mean the axial tension, which is 215, therefore it is safe. So you see how we'll determine the tensile capacity of a section. Alright, so I would need you to take on the second question. You know, we've done shear, we've done bearing, and maybe a little information on how to look for your block shear capacity, and what information do I need to give you on how to obtain your LV, and LT. Okay, so if you look at this now, this is quite different from what we have, and if you check the code of practice under block shear, you will discover that your figure, the figure you would use that actually fits into this particular question is the one that has this kind of shaded portion. Okay, so and the question already told you that you should find suitable pitch and the edge distances. Cool. So the first thing you're going to do is check for the minimum and maximum pitch, minimum and maximum end distances, and from there you can choose what the values would be based on this minimum and maximum value. Choose the recommend a value that you can use acceptable based on the minimum and maximum values for your spacing, which is the same thing as pitch, and then the end distances. So for example, if you obtain 50 for your end distances and maybe 40 for your pitch, it means that you are going to have something like this: 50, 40, and this one also 40. So adding the three together, it means your LV, or yeah, you'll be this will be, it should be about what do we call it now, 130, if I'm correct, 130 or 120 rather. Am I correct with that? It should rather be 130. I think I'm correct saying 130. Alright, so that will be 130. So if you do the same thing for this side also, you from here to here, okay, you have your values already. So from there you can pick your L, LT, or whatever they call it there. Are we clear enough? Are we clear enough? So that should be very, very simple to obtain for you. So thank you very much. If you have any question, do well to reach out to me in the comment section or however it is, and I'll be glad to respond to you. See you in the next video. Bye.